In this video, I want to show you how to use Newton's law of universal gravitation to think through the size of the force of gravity on somebody standing on a spherical planet if you're given the planet's density and its radius, how big it is, rather than given its mass. I'm going to first show you how to use proportional reasoning to think that question through, and second, show you how to use a symbolic solution to answer that same kind of question. So here's the first question. It says, use proportional reasoning to determine by what factor the gravitational force on someone changes when standing on a planet with the same density and half the radius of the Earth. If you have a person of mass m standing on the Earth's surface, someone feels a certain size gravitational force. The question is, if they now go to a planet that's made out of the same type of material, so it has the same density, but the radius is 1/2 the size, by what factor does their weight change? Well, let's start with Newton's law of universal gravitation. The size of the attractive force between any two masses is equal to the product of their masses times the universal gravitation constant divided by r, and r is the distance between the center of one mass and the center of the other mass. And for somebody standing on a large spherical planet, that's essentially just the radius of that spherical planet. So in context, it's the universal gravitation constant times the mass of the planet that you're standing on, times your mass, or the person's mass, divided by the radius of the planet squared. To use proportional reasoning to answer this question, we need to think through how does each of the variables in the equation, things that can change, do they change, and how would they affect the answer? So we don't know anything about the mass. We just know that the planet is half the radius, so it's got to have less mass, but how much less mass? The person's mass doesn't change, so that's staying the same. We put a coefficient of 1 there, and we know that the radius is 1/2 the Earth's radius, so we're dividing by 1/2 r squared. So we need to figure out how much less mass this new planet has that has half the radius. Well, it says it has the same density of the Earth. So how does the mass of something relate to its density? Well, let's go to the density equation. The density of something is equal to its mass divided by its volume. So the density of a planet is equal to the mass of the planet divided by the volume of the planet. Let's rearrange this equation, our density equation, to solve for mass. If we multiply by the volume on each side, the volume cancels out on the right side, and we get the equation that the mass of something, or in this case a planet, is equal to its density times its volume. Well, what kind of object do we have here? A planet, they're spherical, so this is the volume of a sphere. So let's use our equation for the volume of a sphere, which is 4/3 pi r cubed. So instead of v, we'll just put in the equation to calculate the volume, because we know something about how the radius changed, so we want to get radius in this equation. How does the mass of the planet depend on the radius? Well, apparently it's equal to the density of the planet times its volume, which is 4/3 pi r cubed. So now let's go through and do a little proportional reasoning question here. If you're halving the radius, how does that affect the mass? So let's rewrite our equation, and let's just write in the fact that we're halving the radius, and let's think through, if we put a number that's half the size that we're cubing, how does it affect the answer? Well, you just pull out the coefficient, but this is not just 1/2, this is 1/2 cubed. And so the mass will change by a factor of 1/2 times 1/2 times 1/2. That's 1/2 cubed. And what is 1/2 times 1/2 times 1/2? That's 1/8. So if you're halving the radius and you're cubing that number, the answer, in this case the mass of the planet, will change by 1/8. The mass is 8 times smaller if the radius is 1/2 the original size. So now that we know how much the mass of this planet is different than the Earth, let's go back to our proportional reasoning question up here. We know by what factor the mass of this planet changes based on the mass of the Earth. So we'll do that down here. So we know the mass of the planet is 1/8 the original size. The person's mass doesn't change, so we put in a coefficient of 1. The radius is 1/2 the original radius. So to answer, when the mass in the numerator is 1/8, the radius is 1/2, how does that affect the answer? Well, let's pull out all the coefficients to the left and see what they simplify to. So we have 1/8 times 1 on top, that's in the numerator, and we have a 1/2, but that's got to be squared because the radius is squared in the denominator. So it's 1/2 squared on the bottom, so let's simplify. 1/8 times 1 is 1/8. 1/2 squared is 1/4. So we've got a complex fraction, so we're going to take the numerator, which is 1/8, and then multiply by the reciprocal of the denominator, which is 4 over 1. So that simplifies to 4 divided by 8, or just 1/2. So when these things change by these factors, the end result will be, the answer will be 1/2 the original size. So now we can answer the question. If someone is standing on a planet that has the same density and half the radius of the Earth, that means the force of gravitational attraction they feel standing on that planet on its surface has to be equal to 1/2 the size of whatever it is standing on the Earth. So here's an example of using proportional reasoning a couple different times to answer the question that was posed. Well, let's continue to think through this kind of a scenario, but think through how could we develop a symbolic expression, let's say, for the size of the gravitational attraction of anybody of mass m standing on any planet with a known density and a known radius. Well, we're going to have to use a lot of the same equations, right? The size of that force of gravity is equal to our universal gravitation equation. So we've talked about this before. It's big G times the mass of the planet times the mass of the person divided by the radius of the planet squared. But in our symbolic expression, we want to express our answer using the symbol for density and radius. And we've got radius here, we've got the mass of the person, but let's expand the mass of the planet to get density in here, like we talked about before. And that uses our density equation, which we solved for mass. Mass is density times volume. And we said the volume of a planet is spherical, so we put in 4/3 pi r cubed. So rather than just the mass of the planet in this expression, let's substitute in for the mass of the planet using this expression, which includes density and radius. So we're going to put all of that in for the mass of the planet down here. So we get that the size of the gravitational attraction is equal to our universal gravitation constant times the mass, which is equal to the density times the volume, which is 4/3 pi r p cubed, the radius of the planet cubed, times the mass of the person in the numerator, and we have to divide by the square of the planet's radius. So we have a symbolic expression, but before we're done, let's just simplify. Because we have the radius of the planet cubed in the numerator, and we have it squared in the denominator. So this is r times r times r divided by r times r. The r squared in the bottom cancels out 2 of the 3 r's in the top. So if we get r cubed divided by r squared, we're just left over with the radius, just r. And so now we can rewrite this. And I'm going to take all of the things that don't change or can't change, like constants. G is a constant, 4/3 is just a number, and pi is just a number. So I'm going to pull them all out to the left. So we get 4/3 times pi times g. And then what's still in the equation? We have the density times the radius times the mass. And so this would be our final expression, the final simplified expression. The size of the gravitational attraction on anybody with a certain mass m is equal to this if you know the density of the planet and the radius of the planet. So there's the answer. There is the answer to our symbolic expression, which represents the size of the gravitational force on a person of mass m standing on a planet of density rho with radius r. So once we've done that, we could even answer a question, a more complicated question, like 14 down here, that says, use proportional reasoning to determine by what factor the gravitational force on someone changes when standing on a sphere, or whether it's a moon or another planet, with 3/5 the density and 1/4 the radius of the Earth. Remember our first problem in the video, we just said, hey, what if we change the radius? How does their weight change? Well, here we can think through, what if the density and the radius are both changing? By what factor is the gravitational force changing? And these changes, this is approximately true for the moon orbiting the Earth, the Earth's moon. Its density is about 3/5 the density of the Earth, and it's about 1/4 of the radius. And so we're going to figure out by what factor does someone's weight changes if they were to stand on the moon's surface compared to the Earth's surface. Well, to answer this question, we really need to go through this whole process and develop a symbolic expression, which we just did, which tells us how the density of something and its radius both affect the size of the gravitational attraction on a person of mass m. So let's just use what we came up with and do a simple proportional reasoning question. So the size of the gravitational attraction is equal to just some constants all multiplied together times the density times the radius of the planet times the mass of the person. And what's changing when a person goes to the moon? Well, their mass isn't changing, but they're going to something with 3/5 the density. So we put the coefficient in front of our density symbol. And the radius of the planet is 1/4 the size. And the person's mass doesn't change, so that's just a coefficient of 1. And in proportional reasoning questions, all we need to do to figure out how does the answer change, well, we look at the coefficients. We pull out all these coefficients. None of them are in the denominator. None of them are squared. And so if we pull out 3/5 and 1/4 and 1, all we need to do is multiply those coefficients, how each thing changes. So 3/5 times 1/4 times 1. That simplifies to 3 on the top, divided by 5 times 4, or 20. And so the gravitational force will be 3/20 the original size, or if you get that decimal equivalent, it's about 0.15. So that means when the density is 3/5 the original density, the radius is 1/4 the size, and the mass of the person doesn't change, their weight will be 15%, or 0.15 times the original weight on the Earth. So that means when anybody stands on the moon, they only weigh 0.15 or 15% the amount of weight that they have standing on the Earth's surface. I hope this was helpful seeing how you can use Newton's law of universal gravitation to think through problems both using proportional reasoning and symbolic problem solving.